Okay, question before we start? What I would like to show you this using Maple. Can you see my screen? It's all right. It's kind of small though.
Yes, sir.
You can see it, sir.
All right, so let's do. Let's replace this sine x with the. That's what. Check what we did last time. So x just x squared. X. Let's see, square. Where's that sine square thing? Plus minus. Might be the oh. Just x times x. All right. Couldn't find the square. Okay. And from A is 0, B is 1. Okay. And let's see. Let's first divide by, this is what we did yesterday, last week. Say from 1 to, just say the third. Okay, and use, well, I'll explain this one later on. We'll use the, always like, and show you display. Okay. Okay, this is 3, divided into 3, and this is the approximated area. So we know that we compute this, this should be 1/3. So this is the, and the error is just the difference. So a way to make it bigger. All right, let's make it to say 6. And say this is going to be more complicated. We say 100, for example. It's getting denser here, so you can see the, you cannot see the rectangles, but you see that, see the difference here. Between approximate area and the actual area. So it's at least this is 2-digit correct. So 3 is correct. So the difference is the third digits behind the separator. And you can animate. This. Oh yeah, stop. Okay, and what we tried to do earlier is this 1/4 x cubed, right? Plus 1. So say x, let's see, times x, divide by 4 plus 1. Okay, so that's what we have from 0 to 3. It's just not too big. For example, just 4. get this one. Okay, so this approximate area is the one that we derived earlier. Okay. So this I should do this formula here. Plugging N3, N4, N5, and so on. Okay, so it's done automatically in paper. Of course, there's the nth number in the small number, then it's easy to plug, just plug in. But if n is big, then you have a say 10. Okay, so you get the idea. Okay, any questions? All right, if not, then uh, let's do some more of this. And we haven't actually compute this one with the uh, with trig functions, but we can try later on. We'll just do this one here. Say this one. Simple how to uh, express this in sigma form. Problem 12, for example. All right. So what we figure out that the sign is alternating between plus minus, plus minus, plus minus. So it has to do with this power negative one. Let's see. Our k cannot start from one, because if you power one, and negative one power one is just negative, right? But you have positive, so you get to add one. Okay, so that's that takes care of the sign, plus minus sign, alternating sum. And now you can start with this, yes, 1 over 2, 1 over 3. So this is just k starting from, let's say, okay, this is 1 until you end up with 100. So that's for example. Okay. So that's one example. All right. Let's do some more about the area. Okay. All right. So that's okay. The now what we call the section of definite intervals. Okay. Okay. Let's suppose you consider a graph. Okay, for x between A and B. So function f may have a discontinuities, but not too many. Right, so say that f may have discontinuities, but finitely many at most. Just for the sake of convenience of the graph, just consider this continuous. Okay, so it may be a positive or negative. So in general, this should really make use of this one though, make it better. Right? Sorry. Okay, and then the graph looks like there. This is A. This is B. This one. So the discontinuities. So we do the following thing here. Uh, First, uh, we're going to a partition of the interval AB. So what does it mean by partitions? So what we need to do is this is A, B, partition to some parts. The endpoint. This is the x0. This is xn. This is x1, x2, x3. So this is a series of numbers. And that's one. So that's partitions. You divide things. All right. So let's. The second is draw a rectangle. So take a sample of rectangle. Oh, the length of each of this, we call this is delta 1x, this is delta 2x. Okay, so let me write down delta ix is this, or the length of this, the length of the partitions here. Okay. So what we have here is that we have a rectangle. really make use of it. All right, much better. Okay. So this is the of length, say this x I minus 1 x I. So the length is delta I x. Okay. And what is the height? So this is the width. Okay. The height's going to be, well, that's depend on where we take. So let's take a representative. Okay, what is representative? Representative is a point between this interval for each. So this is a representative. So this one called X star. This is a representative of take any point between these two, right? And you may take a random also. Okay, you can take the left end or right end or middle or anything. Okay, so the height's going to be depending on the representative. Okay, so now what do we compute? The area, the sample rectangle, the area of the sample rectangle is just f of x I star times, okay, so that's what we call the okay, so this is the area of the sample rectangle. Okay, we'll do some simulation of this using Maple again. Okay, and then sum. Okay. When you sum, you get this. Yeah. Okay, that is to say, this is the height, this is the width. Okay, so what this represent actually? That represent have this still in the okay, yeah, I think yes. Okay. Okay, so what does it represent? Here's the, and you partition this one. The partition is not necessarily of equal length. Okay. So a sample one should be somewhat here, for example. That is a sample. So the sum is the this area actually. Okay, and okay, so yeah, that's why it's actually. Oh, I should mention that if the sum represent area under the curve and x-axis. Okay? But our equation f, some part of this is below the x-axis, where f is negative. So some part is negative. So this is not actually the area. It's more for that picture, particular picture. If you have a function like this one, so this one is always non-negative. So this sum represents area. Okay. And just to name, this is called Riemann sum. Okay. And all right, so I have mentioned this one, but there is a fourth step here. Uh, take limit as partitions gets finer and finer. Okay, so let me just introduce again some notations. If you have a partitions, this is A, this is B, x0, x1, x2, x3, for example, and your partitions. Partition is P, usually denoted by P. That say xn equals P, right? So there's partitions. All right. You would like to get an idea of the size of the partitions of the partition P is this, just like the norm of a vector. Okay, so the size is actually the minimum of that delta. So the minimum length of this one, the smallest length, that is the what we call the size of partition or the norm of the partitions. All right. So what the for means, take limit as the partition gets finer. That means the size of the partition is get to 0. Okay. So using these notations, what we would like to do in step 4 is taking the limit as partitions goes to 0, as the size of the partition goes to 0, of that sigma of the Riemann sum. Okay, so what we have is this one. So Riemann sum always has this form. And what did they use here? I or index. Or I just write this there. Sigma p. Sigma p means that depending on the partitions. Okay. Of f, that's the representative, the height of the representative times the width. Okay. And note that this is partitions. P is partitions. Next. Okay. And let's introduce again the if limit exists. Then, all right. When we take limit, the sigma becomes there. And the endpoints of the interval, starting from A, initial point, the endpoints, B. It's just X. This becomes the X differential. Can you remember the delta and differential? Okay, and this is called the definite integral. Yeah. On the interval AB. So there goes the story of the definite integral. So it's kind of complicated from the beginning because this tells you how to using this 4 steps. First is the take partitions, and then take sample. You sum all the samples, okay, and then take limit. If limit exists, then this is what we call integral. Okay. So it's definite integral. Just write this down. Partition the interval. Okay. And then we take sample rectangles. Sample one rectangle, and you sum all the rectangles. Sum, and then take limit. If limit exists, then that's the definite integral. Okay, so from the beginning, what we have is the first example. This is 1/3. Why is 1/3? Just remember the process that we compute. We partition, and then we take one sample, compute the sum, and then take limit. That's 1/3. And 2, we compute this one here. Okay. From 0 to 3. That's we get. Oh, we still have to compute limit. Sorry. Let's compute limit now. Let's just copy. Okay. And, oh, sorry. Thanks. There. Uh, wrong. Should. Okay, just rewrite this one. Uh, let this one here. There. Okay. And well, I have to tell you in more detail now. The limit now becomes n goes to infinity. Okay, so equals zero. This well of this term. So what we have here, uh, divide by this for x. Uh, let's see. Did I get it wrong? I guess. Oh, okay. Power 4. This is power 4. Okay. And when you compute this limit, what you have is that 3, this is n squared, 4, 4, so 16, 16, and 4. Okay. Plus, let's see, 3n squared over. But this one goes to 0 because the power, this is power 4, this is power 1. Okay, so n to 4 is much bigger. So this is small, goes to 0. All right, what about this one? All right, denominator is power 4. Numerator is also power 4. So it becomes just the ratio of the coefficients. So what do you have here? Power 4, so just 1. Okay. So this just gives you 3. Okay. So that's the idea of a definite integral. Okay, any questions? Okay, I'll show you some examples using the. Okay. Uh, what's the difference between this one? So I should take this representative. X n minus 1 is an xi. Okay. Okay, so You will compute. All right. Okay. What we compute. Mm, yeah. Okay. So the width is delta I x is delta. What's the height? Well, the height is this representative. So depending on the height, if you take, for example, we say this is left end. If you take the left end, you get this one here, which is the smallest one. Okay. And uh, actually, the area, what you have is fx. If you take the representative is, this is f. So right end, this is right end. So this is right end. And you take also xi midpoint. What is midpoint? Well, that's the average. Okay. So the area would be there. Okay. So that's what we call a representative. So it can be this high, can be this high, or it can be this high. Okay. You can even take a random number between xi minus 1 and xi. Can be random like this. Okay. You see what we have to do with the approximations. Okay, let's read maple. Okay. Now this tells you what's this? This there is upper, lower, random, left, midpoint, right. Okay, so one that I mentioned is this left end, right end, midpoint, random. Upper means that the maximum height. Lower mean the minimum height. Okay. Uh, Earlier we always use the right one. Okay. Okay. Let's do just this. Back to the x variant. X times x. Okay. Between 0 and 1. Okay. And for example, I just keep it 10 and use for example, left first. Okay. If you use left, you get this number 1285. Okay, so this is lower than the actual area. Okay. You can take this more, not 10, but say 50. Okay, So it's getting closer to 1/3. Okay. All right. So let's do this for, say, the right. We use the right. So what about midpoint? Well, you should see if you use midpoint, then you get it's correct to up to 1, 2, 3, 4. 4 digits. Correct. Okay. Seems like the midpoint gives you a lower error, smaller error. Okay. All right. What about uh, the third? Doesn't matter. You get this. You take lower, get that one. So close to 1/3. Okay. And what about taking random? Close also. And let's see what else. This one. Let's go back to that x cube over 4. X times x times x over 4 plus 1. It's, from 1 to 3 is 50, right? Let's use a left. Okay, so 7.8. If you use right, 8.2. If you use midpoint, okay. So it seems that midpoint is better than left end or right end. What about random one? Okay, this also close. Okay. All right, so if you have a maple or wolfram, you can play around with these apps. Right, let's go back to one more. So remark. In step 4, requirement if limit exists, means that the limit is independent of choice, the choice of representative. Of the partitions. Okay. And if the limit exists, then we say f is integrable. So then, so far we have indefinite integral and definite integral. Earlier we have indefinite integral. How the two relate? That's questions. Okay, so we'll explore these questions later. we have the extra sessions for the lecture. So we take an hour worth of the problem session for lecture. All right, questions?